Okay, we'll start with the flip-flops now. I will share the screen. I'm using the whiteboard here. That is the topic which we are going to study. What is basically a flip-flop? Flip-flop is nothing but a bistable switch. It is a bistable switch. What do you mean by bistable? Bistable means two stable states. Two stable states. Okay. For example, this switch is open. It's the open switch. So this is one first stable state. This is the first stable state. It remains open until you close it. Correct. Then this switch is closed. Okay, this switch is closed. This is the second stable. Second stable. So once you close the switch, it will remain in that state unless and until you open it again. So open state is one stable state and closed state is one stable state. Correct. Open I call it as 0 and close I call it as 1. Let us say call it as 0 and 1 in the binary language. So a flip-flop will have either a 0 state or it will have a 1 state. Means it will be either low or it will be high. In terms of low and high, we can call it as low state and high state. Okay. Now, your manual switches. Your manual switches, which we use for turning on fan, tubes, bulbs, turning on and off the fans and tubes and bulbs. We call them as, these are the examples of the flip-flop. This is nothing but a flip-flop. It is nothing but a flip-flop. Okay, so there is very simple example. Whatever switches we use in our houses for turning on the fan, turning off the fan, turning on the tubes, LED tubes, turning off the LED tubes. All these switches, they are manual switches and they are the best examples of flip-flop. Okay, they are manual flip-flops, we can see, not electronic. In the manual flip-flops, we have only two states. Either the fan is on or the fan is off. Okay, either of these two states. But what we are talking about is the electronic flip-flops. Okay, so our topic is not the simple flip-flops. It is the electronic. Now, how to make a electronic flip-flop? That is important. बनवायचा कसा electronic flip-flop? So we need the gates. Okay, I will take the example. This is a inverter gate. Another inverter gate. Okay. Here I apply a battery. So ground plus minus 5-volt battery. Now I also connect one more switch here. Correct. This is the input. Input 1 I will call it as. This is output 1. Output 1 is nothing but input 2. And this is output 2. Correct. So initially we connect this switch. We connect it here. So this is, we are connecting it to 5-volt. Okay, we are connecting it to 5-volt. So this is high. High means 1. So whenever the input to the inverter gate is 1, its output will be 0. So the input to the second inverter gate will be 0. Whenever the input to the inverter gate is 0, its output will be 1. Okay. So when the input is 1, when the input 1 is 1, output 2 is also 1. Okay. Now, if I connect this switch here like this, and if I open it, if I open this part, now this one is transferred from output to the input. So it will remain 1. The input will remain 1. Even if I disconnect the battery, the input will remain 1. And therefore the output will also remain 1. So this will be a stable state. This is a stable state. Correct? Now again I open this switch. Again I open this switch. Okay. Now, instead of connecting the battery, I remove this battery and I directly connect this switch to the ground. So now if I connect it here, this ground means 0. So I'm applying 0 input. So when the input to the inverter is 0, its output will be 1. So the input to the second input to the inverter will be 1. So its output will be 0. So what do you see? When the input 1 is equal to 0, the output 2 is also equal to 0. This is another stable state. This is also a stable state. Now what I do, I disconnect this, I connect this switch here like this, and I disconnect this switch. I make it open. So even if I open it, this output 2 is 0, and this is given back to the input 1. So the input 1 remains at 0. Okay, even if I disconnect the switch, input switch, still the input is remaining 0 because the output is getting connected to the input. So output will remain 0, output 2 will remain 0, and input 1 also will remain 0. This is another stable step. Okay. In this way, you can build a electronic flip-flop. This is the simplest way of building an electronic flip-flop. But here the problem is we don't have any control over the stable states. Okay, we have to open the switch, input switch, then connect the feedback switch. This is nothing but feedback switch. Feedback means we are connecting output to the input. That is called as a feedback. So there is no much control here in this electronic flip-flop. So the modification to this is that we go for another type of electronic flip-flop. We go for another type of electronic flip-flop. And in this flip-flop, what we do, we connect, instead of inverters, I connect a NOR gate. Now let us see what will be the situation. This is a NOR gate. I connect one more NOR gate. This is one input, the NOR gate. This is another input. I call this input as S, this input as R. And then what I do, I connect this output to the second input, like this. So this is an OR gate. This is an OR gate. Now, before we discuss this flip-flop, we must know what is the truth table for the NOR gate. What is the truth table for the NOR gate? When the inputs, both the inputs and output, when both the inputs are 0, 0, the output is 1. When one input is 1, the output is 0. When second input is 1, output is 0. When both the inputs are 1, the output is 0. So output is 1 only when both the inputs are 1. This is important. Okay, only when both the inputs are 0, the output is 1. So this you have to remember. We already discussed all these gates in the last semester syllabus. So I don't repeat that. I've just given you the hint. Now let us assume that this R Yes, sorry. I will draw the truth table now. Now before that, I call this as Q output. Sorry, this is Q output and this is Q bar output. Okay. Now let us see. This is R, this is S, this is Q, and this is Q bar. Okay. Now, when both the inputs are 0, R is also 0, S is also 0. Okay. Then what will be the Q and what will be the Q bar? Now this input is 0, this input is 0. Now, what we say about Q and Q bar? Whether the Q will be 0 or 1. That depends upon whether this Q bar is 0 or 1. Correct? So if the Q bar is 0, then both the inputs will be 0, then the output Q will be 1, NOR gate. So this 1 will be here, and therefore this output will be 0. Correct. So it all depends upon what is the condition of Q and Q bar. So let us assume that Q is 1 and Q bar is 0. When both the inputs are 0, R and S are 0. This we call it as the last step. This is nothing but the last step. Because we don't know whether Q is 1 or 0. Q may be either 0 or it may be 1. We are assuming that Q is 1. Okay, this may not be true. Either way I can also write it as 0 and this will be 1. Oblique. Okay, so this is the last step. Either it will be 1 or it will be 0. Q bar is complement of Q. If Q is 1, Q bar will be 0. If Q is 0, Q bar will be 1. Okay, now let us assume that S is 1 and R is 0. Now if I make this S 1, if I make this S 1, if I make this S 1, then Q is also 1, S is also 1, so Q bar will be 0 and Q will be 1. It will be 1, 0. Let us assume that R is now 1 and S is 0. Now what will happen? R is 1 and S is 0. When R is 1, Q will be 0. Truth table of the NOR gate. If one of the inputs is 1, the output will be 0. So this will be 0. When both the inputs are 0, Q bar will be 1. Okay, so Q will be 0, Q bar is 1. Now if I make both the inputs 1, 1, what will happen? If S is also 1 and R is also 1, what will happen? Output Q will be made 0 and Q bar will also be made 0, because even if one of the inputs is 1, the output will be 0. Now this is not possible, because Q and Q bar should be opposite to each other. Correct. So if Q is 0, Q bar must be 1. If Q is 1, Q bar must be 0. Both cannot be 0 at a time, or both cannot be 1 at a time. So this is a invalid condition, we can say. This is invalid. When R and S are 1, Q and Q bar both are 0, this is invalid, because Q and Q bar should be opposite of each other. So this RS flip-flop using NOR gates has three states, proper states we can say, and one invalid state. The first state is when both the R and S are 0, 0, the Q and Q bar, they are in the last state. That is Q is 1 and Q bar is 0, or Q is 0 and Q bar is 1. This is called the last state. Second state is when S is 1 and R is 0, Q will be 1 and Q bar will be 0 compulsorily. When S is 1, Q is 1. When S is 0, Q is 0. Okay. And the last state is invalid state, because when both the inputs are 1, both the outputs are 0, which is impossible. Q and Q bar should be opposite of each other. They cannot be 0 simultaneously, they cannot be 1 simultaneously. So this is the invalid state. So there is only one invalid state. Other three states are possible in the RS flip-flop. This is a simple RS flip. We can call this as simple RS flip. There is one more category called as clocked RS. That we will discuss afterwards. Okay, if you understood what is RS flip-flop, simple RS flip-flop, then we can move forward or we can move further for D flip-flop. We can move further for D flip-flop. What is D flip-flop? In case of D flip-flop, there is only one input called as D input or data input. But there will be two outputs, Q and Q bar. Now, I can rearrange this RS flip-flop using NOR gate. Same circuit, except I have drawn in a different manner. This is the same circuit which I used in the last discussion. There is no difference. This is R input and this is S input. This is Q output and this is Q bar out. This is your simple RS flip-flop. Now what I do, I connect one more NOR gate here. I connect one more NOR gate. Connect the inputs like this. And I apply only one input, that is D. Okay. Now, why I have connected a NOR gate here? The reason is that this is S input as we know, and this is R input. So R and S will never be 0 both at a time, or they will be never be 1 at a time simultaneously. So if R is 0, then S will be 1. If R is 1, then S will be 0. But both R and S cannot be 0 at a time, or both R and S cannot be 1 at a time. This is possible because of adding the one more extra NOR gate here in between R and S. So let us assume that if D is 0, D is 0, S will be 0. Then R will be 1. This is inverter. This is a NOT gate. Okay, this is a NOT gate using NOR gate. This is a NOT gate using NOR gate. So if S is 0 and R is 1, Q will be 0 and Q bar will be 1. Okay, so if this is the D input, this is Q and this is Q bar. If D is 0, Q is 0, Q bar will be 1. Okay, we can prove that, or we have already proved it. If R is 1, Q bar will be 0, that we know. If one input to the NOR gate is 1, its output will be 0. So this is 0. Both S is 0, this is 0, so it will be 1 here, naturally. So Q bar will be 1. Now if D is 1, if D is 1, means S is 1. If S is 1, Q bar will be 0. If Q bar is 0, and R is also 0, because when D input is 1, the output of this will be 0. So when both the inputs are 0, Q will become 1. So if D is 1, Q will be 1 and Q bar will be 0. So in the case of D flip-flop, we have only two states because the inputs are only one. That is only D input is there. So D input will be either 0 or it will be 1, and based upon that, Q will be 0 or Q bar will be 0, or Q will be 1 and Q bar will be Q will be 1 and Q bar will be 0, or Q is 0 and Q bar will be 1. That depends upon the D input. So what do you see? If D is 0, Q is also 0. If D is 1, Q is also 1. So the output is controlled by the D input. The output is controlled by the D input. If D is 0, Q is 0. If D is 1, Q is also 1. So in this way, we can explain. This is also a simple D flip-flop. Just now we have discussed, before this, we have discussed simple RS flip-flop based upon the same thing. Just I have added one more NOR gate in the form of a NOT gate. NOR gate as a NOT gate, because NOR gate is a universal gate. So you can form a NOT gate also from the NOR gate. And we have connected that in between the R and S input, so that the problem of both the inputs 0 and both the inputs 1. Okay, if both the inputs are 0 in RS flip-flop, the output is in the last state. And if both the inputs are 1 in the RS flip-flop, the output is in the invalid state. So these two conditions are automatically avoided in case of the D flip-flop, because here only two states are possible. When S is 0, R will be 1 compulsorily. When S is 1, R will be 0 compulsorily. So there is no possibility of both R and S becoming 0 at a time, or both R and S becoming 1 at a time. This possibility is not there in case of the D flip. So it has only two steps and only one input, that is called as the D input or data input. So that's all about the RS and D flip-flop. In the next lecture, we will be discussing the clocked RS flip-flop and clocked D flip-flop. Okay, what are the drawbacks of simple RS flip-flop and simple D flip-flop, which we can remove in case of the clocked RS flip-flop and clocked D flip. Okay, we will discuss that. So I will stop here. And we'll complete our lecture here. Next time, tomorrow I will continue with the same topic, RS flip-flop and D flip-flop, but not simple RS. It is a clocked RS and clocked D flip. Okay, thank you.